As the chair of neurosurgery, we explore the ways how we can help our patients. Neurosurgery for decades since its invention has been removing things, and for the first time we're looking to add things back.
This whole space of neural interfaces is also a great way to further the computer sciences, because these devices that we have to build, they're surgically inserted under the skull and placed on brain tissue where they read the activity of neurons. Brain tissue is very sensitive to heat. So you're trying to drive out a huge volume of data from the brain without overheating the brain and processing it fast. And it's really difficult to build hardware and software that can deliver on that degree of performance per watt.
We designed what are called asynchronous chips, so chips that don't use clocks. And so my group is still looking at how we can design more efficient chips without using a clock signal for that to regulate their operation. When we design chips with these principles, it turns out that there are a number of cases where we can exploit this idea to improve the performance, reduce the power consumption.
Halo is the first version of the chip that we built. It can infer hand movement in people who are paralyzed just from brain signals, and for individuals who have pharmacologically resistant epilepsy, it can infer the advent of a seizure and electrically stimulate the brain to mitigate symptoms of that seizure. Scalo is the follow-up system that we've been building, where we would place implants on multiple areas in the brain, read information from all of those areas, and then draw correlations about related activity ongoing in different areas of the brain, and that would allow us to have superior disease treatment options for things like epilepsy.
If you think about epilepsy or seizures, it often starts at a specific brain region and then propagates through the brain network to multiple sites within the brain. One of the difficult components of treating these diseases is not just detecting where they start, but also tracking how they progress and stopping them by stimulating specific regions of the brain. Our distributed network of brain-computer interfaces essentially detects how these signals propagate through the brain and predicts where it's going to move and stimulates the right regions to stop these seizures in their track.
We obviously cannot do this alone. We need cross-discipline collaborations, and mainly with applied sciences and engineering.
One thing I would say about this work is that it's very mission-driven. Ultimately, the success of this field will hinge on two things: building machines that are useful and helping create the next generation of scientists through our postdocs and our graduate students who are well versed in everybody's vocabulary, so that they can then actually build the next generation of machines that are going to be far more capable than anything we build today.